Hi, my name is Owen Slimm, and today I'm going to be talking about ion propulsion. So, what exactly is ion propulsion? Ion propulsion is nothing new. However, NASA and other space exploration companies are looking into using it in new ways. It's basically a high energy electron, which has a negative charge. This collides with a propellant atom, which has a neutral charge, and releases electrons from the propellant atom and results in a positively charged ion. The most common propellant used in ion propulsion is xenon, which is easily ionized and has a high atomic mass, thus generating a desirable level of thrust when the ions are accelerated. It also is inert and has a high storage density. This positively charged ion is accelerated out of the thruster as an ion beam, which produces thrust. A neutralizer expels an equal amount of electrons to make sure the total charge of the exhaust beam is neutral. Without a neutralizer, the spacecraft would build up a negative charge, and eventually its ions would be drawn back to the spacecraft, reducing thrust and causing spacecraft erosion. So how was/is it used? NASA's conventional method of producing ions is called electron bombardment. The propellant is injected into the ionization chamber from the downstream end of the thruster and flows toward the upstream end. This injection method is preferred because it increases the time that the propellant remains in the chamber. Now, currently, NASA uses ion propulsion on a number of satellites orbiting our Earth right now, about 137. In 2007, NASA also launched the Dawn spacecraft, which was tasked with studying the two protoplanets in the asteroid belt between Mars and Jupiter called Vesta and Ceres. NASA used ion propulsion to propel the spacecraft almost 52,000 hours and about 367 million miles away from Earth. Now, NASA's plans for ion propulsion, they're in the process of developing two new types of spacecraft thrusters. As the commercial applications for electric propulsion grow, because of its ability to extend the operational life of satellites and reduce launch and operation costs, this is why NASA is experimenting with this. They are in the works of creating the NASA Evolutionary Xenon Thruster, also called NEXT, and the Annular Engine. So NEXT is a high-power ion propulsion system designed to reduce mission cost and trip time. It operates at 3 times the power level of previous ion thrusters and was tested continuously for 51,000 hours in ground tests without failure. And their patented annular engine has the potential to exceed the performance capabilities of the NEXT ion propulsion system and other electric propulsion thruster designs. It uses a new thruster design that yields a total beam area that is 2 times greater than that of NEXT. So now, is this the future of returning home? Well, there's many different ways that spacecrafts can return home safely. We talked about some of these in Chapter 6, and we will talk about them in Chapter 7. Some of these include free return trajectory, but we are going to focus on constant thrust. Constant thrust is the act of using low thrust propellant in the form of ion propulsion over a longer course of time. The only trade-off for the high top speeds of ion thrusters is low thrust. Currently, ion thrusters can only provide about half a newton of thrust, which is equivalent to the force you would feel by holding 10 US quarters in your hand. Now, while constant thrust is not optimal for takeoff, it can be used during spaceflight and possibly to return home. These thrusters must be used in vacuum to operate at the available power levels, and they cannot be used to put spacecraft in space because of the large amounts of thrust needed to escape Earth's gravity and atmosphere. However, scientists have suggested that using a constant thrust trajectory when returning home could safely be adapted in the future. Thank you for watching. These are my references.